So coming back to the graphs, in this lecture we'll see how to represent various graphs. Okay. So when you talk about the graph data structure, just like we had in the case of a tree, you have got various types of representation in the case of a graph also. So the first one is called set representation, which we have already seen while we were discussing. We will have two sets to represent a graph. The first set will be about the set of all vertices and the second set will be the set of all edges. So that is the first way of representing a graph. You can express the graph in two different sets. The first set being the set of all vertices and the second set being the set of all edges. Next is the linked representation, or to be specific, the linked list representation, where you will be creating a linked list corresponding to all the adjacent nodes of a given vertex. So you will have individual lists that will contain the details of the neighbors of a given vertex. So that is the linked representation. Moving further, the third one is the sequential or matrix representation, which is most widely in use when you are going to represent a graph. So this kind of representation is going to create a matrix which we call as an adjacency matrix. And the adjacency matrix will say whether two given vertices are adjacent to each other or not, and that is the way you can effectively represent a given graph. So these are the three ways by which a graph can be represented. I'll show you examples of all these three. Moving first to the set representation. So as I said, we'll have to maintain two set, the first set being the set of all vertices and the second one being the set of all edges. So if it is a weighted graph, okay, so if it is a weighted graph, still the a vertex set, which is the set of all vertices V, that will stand the same if it is in the case of a weighted graph or an non-weighted graph. But when it is a weighted graph, the set of all edges will have a 3 tuple per pair, which is first it will have the weight of the edge, then it will have the starting vertex and the ending vertex. So this is how a graph is represented using set representation. Okay. So as you can see in this example, so what is the advantage of this representation is that it is very straightforward, it is very simple, and you don't have to spend so much of computation on this particular representation. But if you really have to manipulate a graph, then you cannot use this. Okay, so this is an example of the set representation. So here you can see a graph. Yeah, there are 5 vertices A, B, C, D, E. So the set of all vertices B will comprise of A, B, C, D and E. Next, you have to represent the set of all edges. So if you are going to represent the set of all edges, you have an edge between A and B. So that is represented as A and B. Set the ordered pair AB. Then you have an edge connecting from A to C. That is represented as ordered pair AC. Then another set which is connecting between A and D, and that is represented as ordered pair AD. Moving further, you have DE, CE, BE, and that's it. CD also, sorry, CD also. So that comprises of all the set of all edges. Now, suppose if this graph was connected and it was a directed graph. Okay, so if it was a directed graph and you had an edge which is having a direction from A to B, then you have to write A to B. You cannot write it as B to A. Or you had an edge from E to B, then it should be mandatorily written as ordered pair E, comma B. You cannot write it as B, comma E. Whereas in the case of an undirected graph, whether you write it as A, comma B or B, comma A, both is going to represent the same edge. But that cannot be done in the case of a directed graph, because ordered pair AB and BA are entirely different in the case of a directed graph. So this is how you represent the set. Next is the linked representation. So when you talk about linked representation, you should have a linked list. You should have a node structure as well. So when you talk about the node structure, if you are going to deal with an unweighted graph, which means the edges are not having any weights associated to them, then the node structure will be so simple, which is first you will have to get the label of the node, and then you have to get the pointer to the next node, which is the adjacency list pointer. Okay, so that is the representation. If it is a weighted graph, then you will have to first include a field which contains the weight, then the node label or the name of the vertex, then the pointer to the next node. So this is the node structure for representing a graph using linked list. I'll show you an example. So this is an example. So what you see here is a graph. Okay, so this is a graph, and you have got 8 vertices. So all those 8 vertices are expressed right here. Now you are going to create the list, the adjacency list. It is named as adjacency list of each individual vertex. So starting with the vertex 1, which are the individual adjacent vertices, those vertices which are having a edge connecting with itself and 1. So all those vertices, they are that are having uh, an edge from 1 to itself are adjacent to 1. So first let's start with 2. So there is an edge from 1 to 2. So what you do, you create a node, you enter the node label as 2, and you set the pointer as initially null. Next, you have to add the node 3. Then you will change the null pointer to store the address of this node, which is the node that is being created to store 3. So you add the node as 3, and then again it will be null. Then the final node will be 5. If you don't have any nodes to represent, you can take the last node's pointer as null. It is not necessary that it should be always 2, 3, 5. It can be 5, 3, 2 or 3, 2, 5 or 3, 5, 2 or whatever you wish to. The order of the adjacent nodes doesn't matter at all. Now, moving to 2, similarly, you will have 1, 7 and 4 as the adjacent nodes, 1, 7 and 4. So, you will create the nodes, and you will connect them together, and at the end, you will mark the node pointer as null. So, this will be done for all the nodes of the list, and this is the all these lists put together. It is known as the adjacency list representation of this graph. Now moving further, you have the third representation, which we call as the matrix representation or adjacency matrix representation. So this is found to be the most effective way to represent a graph, because you can implicitly give the information about the adjacent nodes. So normally we take it as a square matrix. So if you have a graph containing n nodes, then the matrix will be of n by n. Okay, so n rows, n column matrix. And this is so whenever you have um, an adjacency between a given vertex vi and a vertex vj, then the node corresponding to, or the position corresponding to vi and vj intersection, that particular value or that particular position will be given a value 1, indicating that vi and vj are adjacent to each other. So I'll give you an example for that as well. So as I said, aij is equal to 1 if there is an edge from vi to vj, and it will be 0 if there is no edge from vi to vj. So this will be more important when you are dealing with not a when you are dealing with a directed graph. So when you are dealing with a directed graph, you cannot say that vi and vj are adjacent to each other if you have vi an edge from vi to vj, then you can say vij is having a value 1. But if you don't have a edge from vj to vi, then you cannot insert a 1 at the position Bji. It will be 0. So that is about the matrix representation. But one more thing that you have to remember is that if you are going to deal with a weighted graph, okay, weighted graph, then this 1 of Aij will be replaced with the corresponding weight. Suppose if there is a path, or there is an edge from Vi to Vj, and we say that Vi is adjacent to Vj, and that edge is having a value 8, then Aij of the adjacency matrix should have the value 8, not 1. Okay. So an entry stores the information whether the two vertices are adjacent or not, and this is also known as bit matrix. When you are talking about only 1 or 0, then you can call it as a bit matrix or Boolean matrix. So this is an example. Okay. So this is an example. You have a graph here, and there is a connected edge from A to B. So you can see from A to A you don't have any self loop. So A to A, that position is 0. From A to B you have an edge. So you can take the intersection of A and B and you can mark it as 1. Similarly, there is an edge from A to C. So you can mark it as 1 as well. Again, from A to D there is an edge. So you can mark it as D. In the case of D, you can see a self loop. This is self loop. So you can see D to D is having a value 1. Okay. Similarly, A to B, and this is an undirected graph. So when you say an edge is there from A to B, the same edge can connect from B to A also. So B to A will also be 1. So this is in the case of undirected graph. When you have a directed graph, then you have to check what is the direction and you have to mark it accordingly. When you have a weighted graph, all these ones will be replaced with the corresponding weight of the edge. So that is matrix representation. Now, so what are the advantages of matrix representation? So matrix representation is very useful and efficient for manipulation. It requires, the only problem is that it requires an n by n matrix. So as the number of nodes inside the graph grows, your matrix will also be grown exponentially. Okay. So it will create a wastage because majority elements will be null. Even if the matrix is too huge, there will not be much of the edges between the nodes, so that may result in a matrix which is called as sparse matrix, which means majority of the elements are zeros. Set representation, it is very simple, it is very concise, but the problem is that you cannot manipulate the data, you cannot change the data, you cannot compute something from the data that is being given inside the set representation. Then this can be used more for some theoretical derivations. Talking about the linked representation, it is found effective for operations like insertion, deletion, searching, etc. But it is not so advantageous when you talk about the time complexity associated with it. And based on the overall performances out of the three, it is found that the matrix representation is the best to represent a graph. So, what are the advantages of matrix representation? The advantage of matrix representation first is that if A is the adjacency matrix of a graph G, and if you can say that sorry for that. So if you can say that there is if you take the transpose of A, that is the adjacency matrix of graph G, and if you find that A is equal to A transpose, then you can derive at a conclusion that graph G was a simple undirected graph. Okay, so if you are given with a graph, if you are given with the adjacency matrix of a particular graph called G, and you are asked to find out what is the type of the graph, then what you have to do is that take the transpose of the given matrix. Okay, take the transpose of the given matrix and equate it or compare it with the original matrix that is being given. If both of them are exactly the same, then you can say that G is a simple graph and an undirected graph. Okay, so when you talk about a adjacency matrix representation, you should be very sure that there are no parallel edges. Okay, there should not be a parallel edge between two given vertices, because parallel edges cannot be represented in the matrix representation. Now, suppose G is a digraph and A is its adjacency matrix, then the diagonal entries of A multiplied with A transpose gives the out degrees of all vertices in G, and the diagonal entries of A transpose into A gives the in degrees of all the vertices of G. So this is another advantage. If you are given with an adjacency matrix of a digraph, what you have to do is that you have to find the transpose of the matrix, multiply it with the original one as A into A transpose. So if you do A into A transpose, you get a value, and all the diagonal entries in that particular matrix will be the out degree of the vertices of the corresponding vertices. And similarly, if you are multiplying it as A transpose into A, then uh, the diagonal entries will correspond to the in degrees of the given vertices. So these are some things that we have to talk about while you are talking about the graph representation. Moving with the graph traversal, that will be discussed in the next lecture. So what you have to do is that you have to create your own graph. Okay. So this is your work for the day. You have to create your own graph, any graph of your choice, not the graph which is discussed inside the lecture. You have to create your own graph, your own weighted graph, your own undirected graph, and a directed graph. Okay, so you have to create three graphs: a directed graph, an undirected graph, and a weighted graph. Represent them using the given three representations, which is, first you have to represent them using set representation, then adjacency list representation, and also matrix representation. That is your first work. Then the second work is that it is regarding the previous lecture. What you have to do is that you have to create a graph and you have to mark all the given terminologies. Okay, mark all the given terminologies like adjacent vertices, parallel loop, sorry, parallel edges, self loop, all the given terminologies you have to mark on the graph. That is your second work. Along with this, you have to submit your lecture note, and that has to be done before the usual deadline. So if you have any doubts, you can contact me. Thank you.